Okay, in this video, we will be talking about the mutual inductance. Okay, when it comes to mutual inductance, you know that there must be two coils. Okay, that means that in the last video, when you are only dealing with one coil, you use self-inductance. Okay, and then remember that of course a coil can have a lot of turns. Okay, so for the same coil, you only use self-inductance. But then now, when it comes to two coils, then you use mutual inductance. Okay, for example, if this is a solenoid, and then this is a short coil, you know that a long solenoid has N1 turns, and then the length of the solenoid is L, and then the cross-sectional area of the long solenoid is L. A short coil with N2 turns is wound around the middle of the long solenoid. And then, please explain the phenomena of mutual induction. Mutual induction occurs when the current flowing in the first coil changes, then this causes a change of magnetic flux linkage in the second coil. Hence, EMF is induced in the second coil. Okay, so you know that when the current is changing in the first coil and then you actually get an induced EMF in the second coil, this is called mutual induction. Just now for the self-induction, you know that when the current of the coil changes, then the EMF is induced in the same coil. Okay, so we call this self-induction. But then this is mutual induction. Okay, so please define mutual induction. Okay, just now when you want to define the self-inductance, this would be your answer. But then when it comes to mutual inductance M, you have to notice that I use E2 and then I use I1. Okay, because E2 is the induced EMF in the second coil, and then I1 is the current in the first coil. So di1 dt is the rate of change of current in the first coil. Okay, so this is mutual inductance because it involves two different coils. Okay, but then I don't have to label so much in the self-inductance because it involves the same coil. Okay, normally we call the second coil as the secondary coil, and then we call the first coil as the primary coil. Okay, but then we don't care about the name so much. Okay, so by the same reasoning, if you don't want to use E2, you can use E1, but then you have to change I1 into I2. Okay, E1 is the induced EMF in the first coil, and then di2 dt is the rate of change of current in the second coil. Okay, so when you are asked to give the definition, you only give this. Okay, or you can also give this also. And then please derive the mutual inductance for the solenoid and the coil. Okay, so first of all, you know that the current can flow through the long solenoid, and then when the current flows through the solenoid changes, there will be an induced EMF in the short coil. Okay, so the magnetic flux density of the solenoid is mu naught and I. Okay, I use I1, okay, because I want to denote the current in the first coil. Okay, I2 is the current in the second coil. Okay, so I use I1. And then the number of turns of the long solenoid is N1, and the total length of the solenoid is L. Okay, and then the magnetic flux linkage of the short coil is N2 times V2, which is N2BA, and then B is this one. Okay, because you know they are coaxial. That means that you know that the short coil is wound over the solenoid. So you know that the B for the coil is same as the B of the solenoid. Okay, so you still remember that the Li equal to NV. That means that the back EMF equal to negative L di dt equal to negative NdV dt. Therefore, you get Li equal to NV. By the same reasoning, the EMF produced in the short coil is E2, which is equal to negative M di1 dt, which is equal to negative N2 dV2 dt. So you know that Mi1 equal to N2 V2. I repeat one more time. Mi1 equal to N2 phi2. By the same reasoning, you can also get Mi2 equal to N1 phi1. Okay? So make sure that you label 1 and 2 properly. Okay? And then phi2 is this one. So you know that you have already derived the mutual inductance successfully. Actually, this is very similar to this. The self-inductance of the solenoid is mu naught n squared A over L. You just simply change n squared into n1, n2 for the mutual inductance. Okay? N1 is the number of turns for the first coil. N2 is the number of turns for the second coil. Okay? Okay. When it comes to define, you just make sure that you want to put negative sign or don't want. That means that I don't really care if you put a negative sign or not. Okay, but then I think this is very personal. Some people want to put a negative sign, but then some people don't want to put. But then for me, maybe I would prefer to put. Okay, because it stands for the Lenz's law. Okay, but I don't think this is a very big problem. But then please ask your teacher. Okay. A small coil with 100 turns of cross-sectional area 1.26 times 10 power negative 3 meters squared is placed coaxially at the center of the solenoid with 3000 turns and length 2.44 meter. What is the mutual inductance between the coil and the solenoid? Okay, so you use the formula to get the numerical value of the mutual inductance. A coil is wound over the middle part of a long solenoid. The mutual inductance between the solenoid and the coil is 2.43 times 10 power negative 3 Henry. If the current in the solenoid is increased at a rate of 14 ampere per second, find the magnitude of the EMF induced in the coil. Okay, so I denote the solenoid as the first coil, and then I denote the coil as the second coil. Okay, so you know that the current in the first coil is I1. Okay, so E2 equal to negative mdi1 dt. Okay, so but then sometimes you know that we really can ignore the negative sign because I only want to find out the magnitude of the EMF only. Okay, and then you have to remember that when it involves two different coils, you use M, which is mutual inductance. When it involves a certain coil, that means that when it only involves the first coil, then you use self-inductance. Okay, that means that actually when the current in the solenoid changes, there will be an EMF produced in the second coil. There will also be an EMF produced in the first coil. Okay, the EMF produced in the second coil is due to mutual inductance. The EMF produced in the solenoid itself is due to self-inductance. Okay, so remember that E2 equal to negative mdi1 dt. E1 equal to LDI1 dt. Okay, because when you are using the self-inductance, you know that you are mentioning the same coil. Okay, or you can also say that E2 equal to LDI2 dt. Okay, but then make sure that they are both referring to the same coil. That means that E is the EMF induced in the same coil, and then di dt is the rate of change of current in the same coil. A coil of 200 turns wound over the middle part of a long solenoid of 1200 turns is shown. The cross-sectional area of the coil and the solenoid is this. If the length of the solenoid is this and then the length of coil is this, find the mutual inductance between the coil and the solenoid. Okay, so actually for this question, you have to measure that the L is the length of the solenoid. Okay, how do you know that L is the length of the solenoid, not the coil? That means that how do you know that L is 2.5 meter, not the 1.25 meter? Because just now when you are deriving M equal to mu naught N1 N2A over L, actually the L is the length of the solenoid where the current flows through. Okay, that means that if you know that the current flows through the wrong solenoid, then this is a primary coil. and then L is the length of the primary coil. That means that L is the long solenoid, not the length of the short coil. Okay, so L is this length. That means that the capital L is this length, not this length. Okay, so you use L to be 2.5 meter, not the 1.25 meter. Okay. The primary coil and secondary coil have a mutual inductance of 0.36 Henry. The primary coil has 12 turns of wire with a self-inductance of 0.82 Henry and carries a current of 5 ampere. The secondary coil has 18 turns of wire. Find the magnetic flux through the primary coil. Okay, so for the primary coil, you know the current of the primary coil is this. And then you are given the self-inductance of the primary coil. And then you know the number of turns of the primary coil is 12. So you can get the magnetic flux through a primary coil. And then I denote the primary coil as coil 1. So everything with the subscript 1 refers to the coil 1. Everything with the subscript 2 refers to coil 2. Find the magnetic flux through the secondary coil. Okay, Mi1 equal to N2V2. You always have to remember, you really have to denote the coil clearly. That means that you can use Mi1 equal to N2V2, or you can use Mi2 equal to N1V1. Only when you denote this is coil 2 and then you denote this is coil 1. Okay, so make sure that Mi1 equal to N2V2, Mi2 equal to N1V1, L1I1 equal to N1V1, L2I2 equal to N2V2. Okay, so this is really important. Please make sure that you denote the coils clearly. Now the switch S is open. Okay, this is continuous. If the current in the primary coil decreases from 5 ampere to 0 in 30 milliseconds, please find the induced EMF in the primary coil. Okay, just now you are given the self-inductance of the primary coil, and then you know that the current is from 5 ampere to 0 ampere in 30 milliseconds. So you can get the induced EMF in the primary coil. And then please get the induced EMF in the secondary coil. So E2 equal to negative di1 over dt. Okay, so once again, you have to remember that if the current in the primary coil decreases, there will be EMF in the same coil due to self-inductance, and there will be an EMF in the another coil due to mutual inductance. Okay, and then please notice that di1 is the final current minus the initial current, okay? Not the initial current minus final current here, okay? But then no matter what answer you will get in the end, make sure that it is positive, okay? Because I only want to know the magnitude. I don't care about the polarity of the induced EMF, okay? So this question, remember that whatever coil which is connected to a battery is called primary coil, and then the another coil is called secondary coil. Okay, two solenoids have a common core. This is solenoid 1 and this is solenoid 2. The rheostat is adjusted to reduce the resistance gradually. Which statement explains what will happen to the components in the diagram? Okay, so when the rheostat is adjusted to reduce the resistance, when R decreases, I increases. Okay, so you know that the magnetic flux due to this increases. Okay, so B equal to mu naught Ni. When I1 increases, the magnetic flux density of the solenoid 1 increases. Okay, so this is wrong. Okay, so when this increases, that means that the magnetic flux due to this increases, and then you always have to remember that the magnetic flux will come out from the north pole to the south pole. Okay, so when the I1 increases, the magnetic flux linkage with solenoid 2 increases. So according to Lenz's law, it should repel this. that means that the solenoid 2 should repel solenoid 1. So when this is south pole, this should be south pole, okay? So that they will repel each other. And then when this is south pole, this is north pole. And then you know that if you look at the solenoid 2 from this direction, you know that the current is in clockwise direction. And then when you are looking at the solenoid 2 from this end, you know that the current is flowing in an anti-clockwise direction. So the induced current is from here to here. That means that the induced current in the load flows from P to Q. Okay, that means that the current will flow from P to Q through the load itself. Okay, no EMF is induced in solenoid 2 if the adjustment is done at a constant rate. If you adjust the rheostat constantly, that means that if I1 increases constantly, then di dt is a constant. So you know that when di1 dt is a constant and m is also a constant, then E2 is a constant. So E2 has a non-zero value. Okay, so this is wrong. The induced EMF in solenoid 2 increases if the adjustment is done at a slower rate. If the adjustment is done at a slower rate, that means that I1 increases slowly. That means that the I1 dt is a very small value. So E2 should be a very small value. So the answer is the induced EMF in solenoid 2 decreases if the adjustment is done at a slower rate. Okay, so by the same reasoning, you know that if I1 decreases, then this should be north pole, this should be south pole. Okay, then the current should be from here to here. Okay, a current which changes at the rate of 1.5 ampere per second in coil P induces an EMF of 0.48 volt in coil Q. Which statement is true of the electromagnetic induction in coils P and Q? Okay, so you know that the EMF in Q equal to mdip over dt. Okay, so by the same reasoning, you can also use EP equal to mdiq over dt. Okay, so you know that the mutual inductance is 0.32 Henry. Okay, so this is correct. An EMF of 0.48 volt is induced in coil Q because the magnetic flux through coil Q is changing. An EMF of 0.48 V must be induced in coil P because the magnetic flux through coil P is changing. No, the answer is I know that there will be some EMF induced in the coil P itself because the coil P itself should have a self-inductance. But then I don't know the value of the self-inductance in coil P, so I never know the back EMF in the coil P itself. Okay, so once again, I want to reiterate that, for example, in this case, if the current is changing in coil 1, the induced EMF in coil Q is due to mutual inductance. But then at the same time, you should realize that there is a back EMF induced in the coil P itself due to the self-inductance. But then in this case, I don't know the value because I don't know the value of the self-inductance, okay? Because it's not given in the question, okay? So this is all in the chapter 17 electromagnetic induction. Thank you.